I'm Shawn, K7ATA. I'm here to talk to you today about antennas. I am not here to tell you what antennas to pick. This might help you decide. I am not here to tell you what antenna is best. That is entirely subjective and up to you. I am not here to tell you how to build an antenna. There's 100 ways, and none of us have that much time. None of us. I cannot tell you all the different ways to build an antenna. I am here today to talk to you about what you need to consider when deciding to build an antenna. Things that will help you get the most from the antenna that you're going to build. I am trying to give a comprehensive overview without going too in depth, as almost every part of this can be multi to dozen hour discussion. This is a work in progress. There will be revisions in the future as time allows. So, practical considerations, not antenna theory, not antenna design. We don't have that much time. I did some brief estimations and I figure I could go for about 26 hours on either one of those topics. So we don't have the time. Antenna, because this is important. We have to make sure we're all using the words the same way. So we're going to talk about common terms. Antenna, device consisting of two electrical conductors for converting electrical signals to or from electromagnetic radiation, also known as radio waves. Electronically, an antenna is actually a capacitor. It's two parallel conductors. All antennas, no exceptions. If you think you found an exception, show me the schematic and I'll show you where you're wrong. Because there aren't any. They don't work otherwise. Number two, any conductive element of a system that radiates electromagnetic waves, intentionally or not. There are plenty of systems out there that radiate RF. Whatever's doing the radiating is an antenna. This is how we define them. Bandwidth. In an antenna, this defines the width of a frequency range centered on a given frequency that an antenna can operate efficiently without being retuned. We usually say that that range is in the 2-to-1 SWR and lower. That's usually, we say, when you go above 2.0 to 1 is when you need to retune. So at the edges of your bandwidth, that's where the SWR is going up. A dipole literally means two poles. Gotta love your Latin there. A simple antenna consisting of two conductors of equal length arranged in a straight horizontal line and driven from the center. The theoretical perfect dipole radiates in a toroidal pattern. Looks like a donut. Gain, this is the one everybody harps on. Gain, get me more gain. Well, you don't. Gain is a measure of directionality in an antenna versus that of either a theoretical isotropic point source antenna. Doesn't really exist, but we have them in theory. They work for math. Or a theoretical perfect dipole. Okay, we measure all gain either in dBi or dBd. And it is important to note that that theoretical perfect dipole has gain over that theoretical perfect isotropic source. So all dipole numbers are 2.5 dB over isotropic numbers. So when you're looking at antenna specs online, pay attention. Are they advertising it as dBi gain or dBd gain? Because I can say, 5.5 dBi, and that's only 3 dBd. which is really important to note. So antenna systems is the entire assembly. Everything from the radio out is your antenna system. It's your antenna, the feed lines, and all your impedance transformers that you have. Okay. Your antenna tuner is an impedance transformer. Your balun is an impedance transformer. And quite often, your feed line itself is an impedance transformer. Okay. You need to keep these things in mind. But the whole thing, everything outside of the radio is your antenna system. And this even includes your grounds. You have to keep them all in mind. Impedance transformer is any device for converting the impedance present on one side of the circuit to the impedance wanted on the other side. Baluns, ununs, any of your antenna tuners, these are all impedance transformers and they do a specific job. Anytime you have impedance mismatches, your radio will complain because all impedance mismatches waste energy and they usually do this as heat. And we all know how much fun heat is in a radio because it's always the active components that radiate that heat. So the finals in your radio are the first thing to go. Feed line. This is the conductors that go from your radio to the antenna with or without the impedance transformers in between. This can be coax, this can be ladder line, this could be two-coat hangers and a stick, keeping them apart. It doesn't matter what it is, it's feed line. Typically, we look at 50 and 75 ohms for coax, anywhere from 300 to 450 for parallel and ladder line. There are some other setups out there that have higher and lower impedances, but those are typically what we will see in amateur radio.
Is there a particular benefit or downside to an impedance, or is it just a matter of?
For a particular feed line, there's no specific benefit for any one system over the other except efficiency. With things like coax, you will lose power to the dielectric in the coax. It will warm up. If you're in some place really, really, really cold that ices up a lot, that may be beneficial. But for the most part, there's no specific benefit to one feed line impedance over the other as long as you are matching your impedance at both ends. Because some antennas are very high impedance antennas, some are very low impedance antennas. You need to match that to your feed line needs to match to your radio. Otherwise, you just get SWR. And SWR is the standing wave ratio. It's a measure of impedance matching of loads and the characteristic impedance of the entire system. And the whole transmission line, waveguide, the antennas, all of the transformers on there. They can all affect your SWR, every single piece of it. I've seen changes out at the very end of an antenna that are nothing more than, cutting 2 inches off of a 130-foot long antenna that changes the SWR enough to go from dramatic improvement to, horrible performance. 2 inches can matter a lot, but at the same time, I could have achieved the exact same thing just by adding a capacitor and twisting a knob a little bit, at the other end of the wire. So SWR is a measure of power coming back to the radio due to reflection in impedance mismatch or something else. And that's the next chart. And this is the first one on your handout. Okay. Very smart guy, Darren, did a lot of math and he verified all this and he left the formulas out there and I went through and did the math and verified these numbers. He rounded off in a couple places, but not by much. You didn't need 3 decimals of precision. But at an SWR 1.0, you're not having any voltage or power come back to the radio. But even a 1.1 to 1 SWR ratio, you're already seeing voltage and power come back into the radio. It doesn't take much. To give you an example, that 1.1 can be a quarter of an inch of wire on an 80-meter antenna. A quarter of an inch is all it takes to change your impedance or your SWR ratio that much. Now, to be fair, a good antenna tuner can eliminate that. But, something to keep in mind, no antenna is perfect. That's why we call them theoreticals. But you can look at this chart and you can know why high SWRs are bad. A 10.0 SWR ratio, more than half your power is coming back into the radio. 67%. That is gonna smoke things. Any questions on this part?
The statement is every antenna is a compromise.
Yes, that's actually in here. Every antenna is a compromise between your ideal and what you can achieve. And that SWR chart explains why we have to worry about it. Because that 60, at a 10 to 1 SWR ratio, that's 67% of your power that's not going out the antenna. Okay, 100-watt base station, you're only sending 36 watts out. The rest is just overheating your radio. So it's important to keep track of. All antenna are made at an electrical level of 2 conductors, even if they are mechanically distinct. This makes all antennas variations on a dipole, 0 exceptions. I have looked and I have looked and I have looked for the theoretical single conductor antenna, and I can't find it. Everybody says, oh, I found a 1-wire antenna. No, you didn't. You just found an antenna where you can't find the other half of the dipole. Because it's there. Guarantee it's there. The antenna will not work if it's not there. You got it?
On the handy talkies, the standard antenna, then they have that little, what do they call, a little wire that you can add on?
Mm-hmm. Counterpoise?
Counterpoise. Does that really make a difference on an HT?
Somewhat. The problem is most HTs, you look inside here, if you actually pull the cover off, there's an aluminum heatsink in here. That's the short half of the dipole. This is literally an off-center fit dipole, but it's driven as a vertical. Okay, that short bit, long bit for the antenna. Yeah, you can add a counterpoise to this, and gee, what do you know? I've got the numbers right inside there. You can add a counterpoise to that, and it can help. But it is important also to keep in mind that quite often you go to aftermarket antennas like this, and this is designed with that short counterpoise in mind, that short half of the dipole. Okay, so this is electrically tuned for the shorter body, which is why sometimes you put that pigtail or counterpoise on your HTE and you're like, it didn't change anything. It's because you've already spent a ton of money on a whip for your handy talkie that negates any benefit that would give you. Most of the cheap ones, like these Bofengs, yeah, you'll see a difference. The high-end Kenwood and Yaesu handhelds, not so much. But yeah, it really seems to matter for the cheap ones. So yeah, all antennas are dipoles, like it or not. They may not be shaped like a dipole, but they are 2 conductors. The antenna itself is the passive part of the system. The system is the antenna, the feed line, which includes all the matching balins and transformers, and the active part, the radio. The radio is what puts the signal on the wire. The system will always try and be in balance. and this is also important to note because this is where SWR comes from. It is the system trying to balance out. Unbalanced systems generally dissipate any excess energy as heat, and they tend to do that at the most sensitive part, the part that can dissipate the heat, and that's usually the emitters themselves, which will be the finals in your radios. The balance is measured as SWR, can also be measured as a ratio of ideal impedance to your expected. If the radio expects a 50 ohm and the entire antenna system presents as a 50 ohm load to the radio, it's in perfect balance. The radio is probably not going to see any power come back. That's a 1.0 SWR ratio. The impedance of an antenna system, which is the antenna and the feed line, changes depending on your frequency. Okay, because it is a resonant circuit. And each resonant circuit has a frequency. And at a different frequency, the resonance in the whole system changes. From that ideal 50 ohm impedance that our radio wants to see, we can go truly unbalanced, highly inefficient ratios. More bandwidth on an antenna means less impedance change for a given frequency change. So if we have an antenna that has a lot of excess bandwidth, turning the big knob just a little tiny bit means we're going to see a very minor SWR change at the base frequency. If we have narrow bandwidth, turning that knob just a little bit means our SWR changes a lot. And then we have to use something like an antenna tuner. We always want our antennas to have a little bit of gain. If we don't have gain, we're doing something wrong. In fact, I do have a device that has 0 gain. In fact, it has a negative number gain. We call it a dummy load. In fact, it's the only antenna type device I have that doesn't have gain. Because again, we are comparing our antennas to either that theoretical isotropic radiator or that perfect dipole. Again, theoretical.
And that perfect dipole has gain because
And it has gain
relative
over
to
the isotropic radiator.
Yeah.
Okay. We always want the antenna to have gain because we're not talking to the dude up there. If you make a contact with your signal going that way, there's awards for that. And they start with NASA. Okay, because there's nobody up there. Well, maybe the ISS guys, but they're only going to be right there for 30 seconds.
Reflect back down and get the guy next to you.
Yeah, well, that's another different game. I've done EME. That's a hard road to hoe. Okay, so we want our gain, and gain we usually talk about in a horizontal fashion. It's important to keep that in mind, even though I didn't write it in here. Gain, we're usually talking horizontal because we're not talking to the airplanes or the guys on another planet. And if we are, we're not talking to anybody horizontal. So that's still gain. Okay, gain is just directionality. How much of your signal is getting sent in the direction you want to talk to. Antennas can be constructed to operate in multiple frequency ranges or bands. Okay, by carefully choosing, sizes and their electrical properties. We can make a huge antenna that covers all the bands with a whole lot of bandwidth. But the flip side of that is that's an expensive thing to build. And an all band, really wide band antenna is huge. It's huge and it's expensive because that's a lot of copper. When building an antenna, the first thing we have to determine is what frequencies we're going to use it on. If you know where, what bands and what frequencies you're going to use the antenna on, that tells you what your requirements are for size. Well, it tells you what your requirements are for resonance, and size is determined a lot by that. Then we decide, are we trying to talk to everybody? Or are we just trying to talk to one person at once? Are we trying to be omnidirectional or unidirectional? Because that again changes the antenna we built. If I have one repeater on a hill 50 miles away that I want to talk to and I don't care about anything else, that's an entirely different antenna than if I want to talk to all the repeaters around me. And that changes the design of the antenna. It changes which antenna I decide to build. Am I doing DX? Am I doing NVIS? Am I doing other things? All things you have to think about when you decide on your antenna. And then, of course, sometimes you're mobile. I guarantee the mobile antenna on Tom's truck or Roland's car or my car is different from the stationary antenna operating on the exact same bands that we have at our home stations. I couldn't put my UHF antenna on my car. There's not enough mount point on my car to put that antenna on. That antenna is 10 feet tall. I don't even want to think about the low bands. Hey, Tom, how many screwdrivers are on your truck? Okay. All antenna design is a compromise between the frequency you're using, how you're using it, and the physical requirements of your site. Okay. All antenna design is compromise. It's how you compromise that decides what you're building. With the exception of a perfect dipole, all antenna are going to have an impedance that is different from that expected by any solid state transceiver. And more importantly, is also going to be different from the feed line. So you need to have some kind of impedance matching transformer between your feed line and your antenna, unless you have a magic dipole. The other kicker is if you don't have a impedance transformer between or impedance transformer or an isolator between your feed line and your antenna, your feed line is part of your antenna. No exceptions. Okay. Impedance transformers come in a bunch of flavors. We got Balins, we got Ununs, Balvals, which nobody ever talks about because sometimes you have a 200 ohm balanced antenna that you want to feed into 300 ohm balanced feed line. Do you make impedance transformers for those? They're just, a lot of folks call them all Balins. It's not accurate, but it's easier to just say impedance transformer. All of our line isolators are also impedance transformers normally, but it works. Common mode chokes. They're often confused with things like Balins or impedance transformers. They're not. The entire point of a common mode choke is to, and by the way, these are only used with coax. They are to prevent the signal from running down the shield of the coax from the antenna, which would give you a very unbalanced antenna. Usually they're either things like an ugly Balin, which isn't really a Balin, it's a common mode choke. It's just, a bunch of turns of coax around a form. All that's there to do is stop the RF from progressing down the coax. It could be a bunch of ferrites clamped on. Those work too. You can do impedance transformers that way, but it's a secondary function. But knowing which is a common mode choke and which is a Balin helps, because you're often going to see both together. Generally, the common mode choke is on the feed line side. The Balin is on the antenna side. There may be another Balin at the radio end, but that'll be separate.
say that they all require some form of impedance transformer.
They all do.
So in a standard mobile setup, is it hiding somewhere? Like I don't.
Built into the antenna.
Oh, okay. So it's just part of the antenna. Got it.
This one, it's right.
Ah, okay. It's the
impedance transformer is in here.
it's the coil. Oh, got it. Okay.
Okay,
Cool.
it could just be a single coil. It could be a complex transformer, but there is something to transform the impedance from the transmission line to the antenna.
Sweet.
And in this case, it's at the base of the antenna.
Right.
And if you look at multi-band verticals, there's multiple impedance transformers in that antenna.
Right.
Okay, multiple loading coils. A loading coil is just an inline impedance transformer. Mathematically, we have to treat it like that. Where you can't solve the math. To be clear, unless you have some form of transformer at the interface of feed line and antenna, your feed line is part of the antenna. Okay. This is why you get so many people saying, oh, with this antenna, you have to use this length of coax. That's because that length of coax is what's needed to complete the antenna. Okay, there it's like, oh, we didn't design it right, but we figured out that if we put this much coax on it, the whole thing works really good. Well, that's because you didn't balance your antenna in your design. The easy solution is to put an impedance transformer or a common mode choke up there and not worry about it, and then balance your antenna that way. And again, even a perfectly balanced dipole wants some form of choke or transformer, because otherwise your feed line becomes part of the antenna. And even if you are using a perfectly balanced feed line, like 300 or 450 ladder line, with no choke or anything at the top, it's not a dipole as so much as it's like a double L or a doublet. And that changes the antenna and changes how it works. So if you do the math on a dipole and then just connect it directly to the feed line without putting anything between them, your math is useless. Okay, things to keep in mind. The other end, this is important. Unless your shack is outside, you're going to go through a wall or a window. You have to figure out how to get from your radio to the antenna, unless you're using like a magnetic loop on the other side of the room. One of the few antennas I know that works just as good inside as outside, which is to say not very. Wall penetrations. We need to be concerned about things in the wall, like the studs, the electrical wiring, the plumbing. Trust me, hitting any of those is bad for putting your antenna in. If you're drilling holes through your studs, you're weakening the wall. If it's a load-bearing member, well, when is the house going to break? Yeah, have you ever drilled into your plumbing? Makes for all sorts of fun, doesn't it?
3 days later.
Yeah, it's not a cheap fix either. It's never a cheap fix. I would rather drill into the Romex in the wall, because that I just tear out a bunch of drywall, run some new Romex. Plumbing, you have to worry about everything below it because water goes down. Yeah. Ask my dad about the time he drilled into the sewer line with a 2-inch core drill.
Don't hit the stinky plumbing.
Yes. It was a shitty day. Okay. Yeah. So you have to think about where you're drilling. You have to think about how you're getting your coax or your ladder line or whatever out. You have to also think about weather tightness. If you're just sticking coax to the wall, you have to make sure that the water's not going to run along your coax and drip down in the wall. There's nothing more fun than finding out you've caused the black mold. Okay. You can do window inserts, but you also need to figure out how it affects the air tightness. Modern efficient homes don't want air leaking in and out through the windows. And if you have a window partially open, guarantee you've got air leaking around the panes. Triple pane window with a free air path. It doesn't do any good. So you have to figure out both sides of the window, not just where the coax is going through, but the other side where you've got that cap now. That air can get in and out. Okay. And then we have to talk about electrical safety real quick. Anytime you have an antenna above the ground, you have a greater than zero risk of electrical problems. Lightning is the first and foremost we all have to think about. Weather like this, where it was hailing earlier, and how many of you disconnected your coax before you came here? Mine's all shorted to ground. Because the last time I forgot to do that, the lightning strike took out one of my radios. Lightning protection, the RF and safety grounds, we have to consider those. They're actually really easy when we're doing wall penetrations. If you build a dedicated wall penetration with multiple coax feeds through it, odds are you have a metal plate on each side. You're going to be grounded between them, ground them on the outside. Put a new ground rod into the ground. Do not tie to the house's electrical ground.
Shawn,
Yes.
I think you might want to check the National Electric Code on that.
I'm talking specifically for RF. You have a separate safety ground.
I think you'll find that the National Electric Code says that all ground conductors need to be bonded together on the site. Just something you want to check for future.
I will check with the NEC on that one, but I'm specifically talking about RF safety grounds, not electrical grounds.
Oh, okay, thank you.
Yeah, I have a comment on that.
Okay.
I have a separate ground rod for my antenna systems, and then I have the lightning protectors on there. If you get a direct strike, you're screwed anyways. But I got just for the antennas separate ground. Of course, the radio probably goes through the ground on the house, but so I ground to that common ground rod from the radio and the antenna and everywhere else. That's a separate copper coated ground rod.
It was an interesting read, if I could inject this really quick. When I was putting my antenna up on the house and in the tree, I wanted to read about lightning protection. And I went onto one of the sites that sold the little ones we use up to commercial. And at the very end of the site, it said, please read. And it said, please understand, if your house gets a direct hit with lightning, the last thing you're going to worry about is your radios. It says your appliances will be gone. Most of your Romex will be disintegrated, and on and on and on. So whatever effort you do, if you get a direct hit.
And it's important to note that we're going to talk about that here.
Yeah, I have polyphasers, I guess they call them, but
Yeah, me too.
so I mean, but you get a direct strike, you're screwed.
You're screwed.
Since we're here, lightning protection comes from a device that shuts the high voltages of the strike or a near strike to ground. Okay, this could be things like spark gap devices, metal oxide varistors, gas discharge devices, and there's a bunch of other less common ones like parallel varactor gaps and things like that. Even with great systems installed, disconnect your radios because none of these devices trigger before the damaging voltages already exist. Okay, your radio with an indirect strike, your radio is still fried. Okay, the difference being is that if these things are installed correctly, which is on the outside of the wall penetration, the fire stops there. It doesn't come through the wall and into the house. Okay, that's some, yes, for a strike that's 2 miles away, odds are you're fine. But if lightning hits into your yard and misses your antenna by 50 feet and it's connected to your radio just became an anchor. So did probably your TV, your sound system, half the computers in your house, maybe all of them. But at the point these start doing voltage arresting, enough power has traveled down that coax into your radio that it's at risk, at the very least.
Our neighbors got hit across the lake. We were on the deck watching the lightning hit, and it hit her 150-foot Doug fir, took out all her computers, took out that dog fence, underground dog's fence, all of her electrical system in her lake house and everything, and busted the tree in 4 sections.
Oh yeah,
Yeah, it's pretty amazing.
There's a lot of power in lightning bolt. There's a lot of power in a lightning bolt. And it's scary to think that that's just power Mother Nature's getting rid of because it's excess. Yeah. So surge arresters plugged into your outlet is not going to protect your radio from lightning strikes on the coax. I don't care how big a surge arrestor you have in your power supply. It doesn't protect the coax side of the radio. It'll protect the power supply, but not the radio. Yes, the invisible gorilla. That's what I call it. You hear people talk about bandwidth and they go on and on and on about trying to get more bandwidth out of their antenna. It's hard. Pure and simple. Bandwidth is hard. And more importantly, bandwidth is expensive. Did the math, and it's on this handout, bottom chart here. 28 gauge wire on the 80 meter band, 3.5 megahertz, 0.17 megahertz of bandwidth, 170 kilohertz. In order to double that, you have to add 2 zeros to the diameter of the wire. You have to go from 28 gauge to 1 inch in order to get 300 kilohertz of bandwidth. Cage dipoles are
The cage dipoles.
yes. The cage dipole is the magic workaround for that. But a cage dipole with a 12-bar cage dipole literally costs 12 times as much to build, plus your separators.
It's true.
You're running 12 times as much wire. I don't care what wire you're running. So bandwidth is expensive, period. No ifs or buts. You could take, a 1-inch pipe and wrap it with foil. That's the exact same as using a 1-inch pipe. But that's a lot of foil.
Comment.
Comment?
Yeah. We all have to remember that the electrical signal runs on the outside of the wire and not on the inside. So that explains the diameter.
Yeah, it's diameter, not mass.
Mhm.
Okay, it's ampere carrying capacity, it's surface area. The more surface area the antenna has, the more bandwidth the antenna has. And we can simulate surface area by doing something like a cage element. But again, we are exchanging dollar bills for bandwidth. And by the way, there is no return from that. You can't get your dollar bills back.
Copper is not cheap now.
Copper, no, it's not cheap.
Nuts.
Try finding pure copper wire right now. Everything coming out of China, which means, Amazon or most of those sites, is copper coated steel. Even when they say pure copper. Okay, was in a hardware store a few weeks ago. Spool of wire on the shelf. Took a magnet off of their shelf and it stuck to the spool. I'm like, that's not copper. Why is it priced like copper? Surprised them too.
I bought a 25-foot roll of 12-2 for my cabin. It was $47.
Yeah.
25 feet.
Almost $2 a foot for Romex. So That's the invisible gorilla. It takes roughly adding 2 zeros to the diameter number to increase the bandwidth by 100%. To double the bandwidth, basically. So to go from 300 to 600, I will have to add another 2 zeros. "100-inch diameter would only give me 600 kilohertz of bandwidth on the 80-meter band." I don't even want to think about how much copper would be involved in that, even with the cage dipole. So
You need surprisingly few conductors to play the bandwidth game.
to play the bandwidth game, yeah, to build a cage dipole, it's actually surprisingly cheap. For
A
number,
4-conductor cage is not as good as a 12-conductor cage, but a 4-conductor cage is,
still better than a
good.
single conductor.
yeah, it's vastly better.
Mm-hmm. So that's the hard part of the talk right there. There's a bunch of math that goes behind a lot of the statements, but that's the hard part of the talk. Now we get to actually talk about antennas. Okay. 2 pages, 2 slides here. We're just going to briefly skip over these real quick because we're going to talk about these more. I'm just listing the antennas that we have here. We're defining an end-fed, whether we call it a ZEP or a long wire, whatever. It's an antenna we drive from one end of a really long wire. Okay. Quite often multi-band, there's going to be a counterpoise because it doesn't work if there's not. We will find the other half of the dipole. Okay, an off-center fed dipole is very similar to an end-fed. In fact, they're really the same thing. Any end-fed antenna is just an off-center fed dipole.
Very upset.
Just very off-center. That's really what it is.
Very off-center.
Yes, but it's still there. And there's always an impedance transformer in there too.
Yes.
And more importantly, that impedance transformer is between the 2 halves. Electrically, it's in between. So you got your basic half-wave dipole, 2 conductors, equal length. Each side is a quarter of the length of the actual wavelength you're working for, giving you a total of a half wavelength of antenna. Folded dipoles, these things are fun. You go a full loop, full wavelength loop of wire, and you flatten it like a dipole. These things actually work really good. In fact, that's what almost every FM broadcast station uses. And they usually use a helical version of it, which gives them a circularly polarized signal. Anybody that wants to come up to Cougar next time we go up there, we'll point out a whole bunch of these things.
Sunny day this time. Sunny day this time.
Oh, yeah. We had a sunny day the last time we were up there. We could see all the way to from Tacoma to Seattle, Bellevue, Issaquah.
Have they built any houses down that cul-de-sac yet?
Nope, they're never gonna.
Good Lord.
They're never gonna.
Not infrastructure for nothing.
Well, they wanted to sell them for about $2.5 million a piece. And somebody said, I don't want that interrupting my view. So they bought all the lots.
Wow.
The inverted V or just slot V. These are basically dipoles with the ends closer to the ground or just slightly closer together than they would be if they were perfect. Vertical antennas, whether they're single band or multi-band. We have, a radiating element straight up and a horizontal ground plane or less than horizontal in some cases. But, they provide all sorts of benefits and drawbacks too. Loop antennas, sometimes referred to as sky wires. It's an antenna somewhere off the ground, runs in a full wavelength loop, usually driven from either a corner or the center of one side. Different effects for both. But they're useful if you have a lot of space because loop antennas do not come small. A full wave loop for 80 meters, well, takes off 80 meters. and then wrap that in a box or a circle. That's the minimum space you need for that. You know, go to the longer bands like 160 or, oh geez, some of the new bands. I would love to put up, well, I would love to be legally able to put up a 2.2 kilometer loop. By the way, the legal restriction on those antennas is 50 feet for that band. 50 feet. 1 watt EIRP.
Sean, I'm referring to that band. Can any amateur go on there? Do they still have to request a specific experimental license for that?
The band is open, but there's only an extra allocation for it.
Is that true? It's only extras?
I think it's only extra. There might be a general, but I'm pretty sure it's only extra.
There is a
Either way,
distance.
you still have to register your location and verify that you're not going to be harmfully interfering with your power services. Amusingly, I registered mine before PSE started running the smart meter systems out here. And they sent me a really nice letter saying, hey, can we please ask you not to do that? No. Because once I receive my allocation, they can only request, they cannot stop me from using it.
Does that mean when you move, you're losing that allocation? Because it's
Yes.
site specific? Yeah.
That's site
It is
specific.
very site specific.
Okay.
And when I move, I will lose that allocation.
Yeah,
That's like-
extra advanced and general.
Oh, general does get
Yeah,
it.
for
Awesome.
both 2200 and 630.
Okay.
So those of you with general tickets,
Have fun.
file your request and get turned down by PSE probably.
So, you know, magnetic loops, these are those little tiny things. They work. I built a few. Are they fun to use? A little bit. Are they easy to use? Oh, heck no. It is far and above the most fiddly antenna you will ever use. My magnetic loop, which is built for 20 meters, I have a bandwidth of 1.2 kilohertz. Think about that for a minute. Your sideband voice signal is wider than that. So just by keying up my radio, I am exceeding the bandwidth of that antenna.
Basically CW only.
Well, you can make sideband contacts with it. It just sounds kind of crunchy.
Well, yeah, I mean, you think about the bandwidth of single sideband signal and the lower, 500 hertz don't carry much power.
Yeah,
and,
they don't carry hardly anything.
and above 1800 hertz, not
Yeah,
that much power.
I basically, it clips the very top of my audio with a bad SWR.
It probably
So-
sounds pretty weird on the other end.
It sounds muddy at both ends.
Yeah.
But if I make one contact on a frequency and I see a guy 3 kilohertz off that I want to talk to, I tune my radio and then I tune my antenna. And then I use the antenna tuner in between.
It's kind of, so I'm just curious, there's a practical matter, Shawn. You dial to whatever frequency you want.
Mhm.
There's some guy who's calling CQ. Now you've got to tune up on that frequency.
Yep.
Which is kind of annoying to everybody who's listening.
Yes, it is.
I never really thought about that.
Yeah, those antennas are a pain in the ass. They're fiddly, they're great. Noise, there is no noise. The noise floor is so far down below what the radio can hear, it's not funny.
Interesting.
Those things are so noise immune, it's just ridiculous. The Yagi Uda, or as everybody calls them, Yagi antennas. Amusingly, it was actually Uda that invented the thing. Yagi was just the guy that presented it to the folks in the US. You go to Japan and you ask for a Yagi, they go, what? It's an Uda antenna.
Well, they're both Japanese.
I know, but it sounds like food.
Yeah. It makes me hungry for ramen. Guess what?
Little
I'm having
soy
for dinner
sauce.
tonight?
Yeah, pretty tasty.
But the big thing with the Yagi Uda is these things are directional. The more elements you put on them, the more directional they are. I've seen Yagis with 22 elements, single band antennas with a 5-degree beam. They were incredibly directional, and we used them for point-to-point data radios. And we were sending 15 gigabit across that. And yeah, it was at a much higher band than we get to use here. Or than we normally use here. I think we actually have allocations up in the 15. But they're fast. They're directional. They're tight. And if you want to talk to the guy on the other side, you have to turn the whole antenna and get fiddly with your aiming. And the more directional it is, the bigger that gets.
Shawn, there's plenty of amateur allocation up above.
Oh yeah, there's plenty of average.
Everything above 275 gigahertz, fair game.
Yep. And then of course we get the log periodics. These things look like Yagis. Everybody looks at those and goes, "Oh, it's a Yagi antenna." No, it's not. It's a log periodic. It looks like a Yagi. It acts like a Yagi. The biggest difference between a Yagi and a log periodic, the log periodic is multi-band. And you could stack a whole lot into a log periodic. And they can be a lot of fun to use. But they suffer the same drawbacks as a Yagi. They're directional. And if you want to talk to somebody else, you have to get fiddly with the aiming.
One comment on that. I use that for satellite work. And they really, if you look at them, really don't have a reflector like a Yagi.
We're going to get the pictures. So,
yeah.
So now we get to the picture part. Here's the fun. We talk pros and cons. Dipole, 2 even elements. There's a baleen in there. In this case, it's actually just an isolator since it's a 1-to-1. We could be going to coax or ladder line. So pros of a dipole. These things are inexpensive for all considerations. They are the cheapest antenna to build. They're simple to build. This is why they're cheap. It's just 2 wires and a little either isolator or a transformer. Couple pieces of rope, couple pieces of insulator. The insulator doesn't have to be anything special. I've bought a $1 cutting board from a dollar store, chopped it up with a Sawzall, drilled a couple of holes. There's your antenna, isolator and insulator. You can hang it off of that. No problem. The cons of dipoles, they need a lot of space. A good dipole needs enough room to be half a bandwidth long and half that high. So dipoles need room. You need to be able to suspend them. You need to be able to work on them. But that's the biggest con is dipoles needs room. That and a single band dipole is exactly that, single band. Multi-band dipoles, they're bigger. The end-fed wire antenna. I don't care if it's an end-fed half wave, end-fed ZEP, or G, an off-center fed dipole, because they're all off-center fed dipoles. The counterpoise, that's just the other side of a dipole. It's an uneven dipole, but yeah. Long wire antennas are usually multi-band. They're frequency agile, they're band agile, they're usually pretty easy to build. They're also relatively inexpensive, excuse me. The cons is you absolutely need a tuner with an end-fed wire. Whether, it's a ZEP or a 132 or anything else, you need a tuner because you are never going to get a good match on any frequency. It's going to be close in a lot of places, but it's never going to be great. You need a tuner, period. Okay. So expensive because a tuner is part of the equation. Okay. They want lots of height. They want lots of space, just like the dipole. Folded dipole. Okay. It's a loop that's been squished flat. These things are actually really efficient antennas to build. If you have the room for a dipole, build a folded dipole. You won't regret it. In most cases, the performance is going to be about twice as high. And they're much better at rejecting noise, especially local noise, because they're a full loop. And that full loop just makes them a lot easier to work with. Okay. They are simple to build. You know, they literally use twice as much wire as a dipole. And then a smidge over that, but you get what you pay for. And in this case, they're definite bonuses to having a folded dipole. A multi-band folded dipole, there we start getting really expensive. But again, they're relatively simple to build, easy to work with. The cones, they need just as much space as the dipole and a little bit more structure to support them. The good old inverted V, also referred to as a lazy dipole sometimes, because I didn't feel like getting the ends up in the air. It's literally just a dipole that droops. 60 degrees greater at the center. That works really good. The less in plane you are, the more weird these things get, though. You can have lots of nulls on an inverted V. Most cases, those nulls don't matter. On a well-built inverted V that's truly well lined up, the nulls point straight down. You are not talking to that guy. I've never tried to talk to that guy, so they are easy to build. They are easy to build. You just need one center support, go straight up. I've seen squid poles used. I've seen all sorts of these things set up. The ends 4 inches off the ground on a 20-meter inverted V works just fine. Just get them up in the air, in the middle. You can get some good DX on these antennas. So they're easy to build. They're inexpensive, no more than a dipole itself. Usually no more than a dipole, unless you want to buy, really fancy squid poles or something to lift them up. They need slightly less room than a full dipole. You don't have to go quite as wide. But the cons, they're a bit harder to tune. They're a bit more sensitive to tuning. And sometimes conditions change and your tuning's changed. A inverted V here in the summertime performs significantly different than an inverted V in the wintertime. Because just ground conditions. Because your ends are close to the ground. Highly saturated ground conducts different than dry ground. And your performance will change. And if you're out of line or one end hangs more than the other, you've changed your performance of the antenna and the nulls are going somewhere weird. It gets weird. And then, of course, there's the version of those that's sloped, intentionally so. And those can be really directional. Sometimes very unintentionally so. But sometimes if you plan for it, you can get some great performance. I've talked to guys in Siberia over the pole with one of these. It was a fun contact. He used a huge Yagi, but
Probably using ice as the antenna.
yeah, could be. Next, please. The good old vertical antennas. I mean, we've all seen these things. Half of us have them on our cars. Some variation on them. Surprisingly enough, that looks a heck of a lot like the same model antenna we use up on top of Cougar Mountain. In fact, it almost certainly is the same model we use on top of Cougar Mountains, and that's what I was searching for when I found the picture. You can get a lot of gain out of vertical. That one, that specific one pictured is a multi-element vertical. There's actually multiple 70 centimeter elements stacked right on top of each other. So it's an array antenna. Complex verticals. Vertical element, horizontal ground plane, both single and multi-band. They come in a lot of varieties. You can get them from HF bands. What's the biggest HF vertical you've ever seen?
Friend of mine had a quarter wave 160 meter dipole in his backyard with a huge underground wire ground.
Yeah.
Oh, well, it's about 450 meters.
Yeah, you can find huge vertical antennas. But the big problem with verticals, space saving. I mean, footprint on a vertical, this and a couple of guy wires somewhere else. But low noise, they're generally relatively easy to put up there. Screwing a vertical into the eaves of the house, not a problem. Cons, well, limitations on height. Really stringent grounding requirements with these things. Because from up in the air, they look like lightning rods. You will note if you look at that picture real close at the very top, it's got a big metal cap on it. They decided if Mother Nature's going to treat this like a lightning rod, let's build it like one. There's a core through that's tied to the ground in the middle. The antennas up on Cougar Mountain get hit at least once a year. It's not uncommon for us to see direct strikes up there.
Everything survives, it's all okay.
Yeah, that's exactly it. A few years ago, I went up there and helped replace one of those verticals that had taken a few too many strikes. And the cap at the top of the antenna showed it. There are like a half a dozen spots where it's obviously melted the metal slightly. But that antenna survived 25 years up there. This is the Skywire, the loop, big guy. Single conductor antenna connected to the feed point at both ends, elevated off the ground, arranged in a loop, a box, a hexagon, a circle, something. Triangle even. They work. Their performance varies depending on how high they are above the ground and the shape you put them in. But they can be really useful antennas. I've seen these things laid across the fence top in a backyard. Yes.
Oh, yeah.
Really good.
6 feet high on top of a wooden fence.
Nice
In a
AGIS.
neighborhood where nobody could see it. He was using a 14 gauge wire. He just ran a lot of wire in a big loop around his backyard, hooked it up to a tuner, pissed off all of his neighbors, and they couldn't figure out how he was doing it.
What was he doing that pissed off his neighbors? That's what he was doing.
80 meters.
Kilowatts.
No, actually, he was making his neighbors mad because they were looking for an excuse for the HOA to get him in trouble.
Next neighbors.
They even threw a fit about his satellite dish.
Can't do that anymore.
They can't bitch about that anymore either. But until we get the Amateur Radio Parity Act passed,
We're getting closer.
we're getting closer. But until then, loop hidden on top of the fence.
This is the one we had on top of City Hall, wasn't it, in Carnegie?
We had one of these on top of City Hall.
Yeah, and it wouldn't work because of all the noise. It'd be nice to be able to
Which
test
is
it.
really funny because loops are supposed to be noise resistant.
Well, we couldn't help it because Carnation City Hall is the Ghostbuster building.
I'm really certain it is because we measured.
Oh, Jim
that
and I verified that
Yeah.
walking around town.
Yeah, I helped with some of that.
Miller's
too.
terrible too.
Oh, yeah, Miller's.
Carnation City Hall, you get 20 feet from the building and your noise floor just drops.
Yep.
Inside the building, some days we were plus 30 dB over.
That transformer that was outside of Pete's, right across from the city hall.
Mm-hmm.
That
That thing was horrible.
terrible.
It's toxic. The con with loops is they're very omnidirectional. And most folks don't think of that as a con. But when I'm trying to make a contact a guy over there, and the guy over there is having a conversation with somebody even further over there, and he's got a lot more power than the guy over here, I can't hear the guy over here. You know, if I want to talk to a guy west and the guys out east are really loud, all I'm going to hear is the guys out east. Okay. And of course, these things are tuning sensitive. You have to use a tuner with them. Usually they work better with a tuner at the antenna. And that tends to be expensive. But again, tuning sensitive. They're usually very fine gauge wire. The biggest one I have ever seen was 14 gauge. So not a lot of bandwidth.
You remember what gauge we used on top of City Hall?
16.
What, 16?
Ah, yes, the mag loop. Vertical loops, mag loops. This one picture is only a meter off the ground. And you can easily go halfway around the world with that thing. They're terrible antennas. They're fiddly. I mean, they're fun. You can build one in a day, and you don't even have to get on a ladder. But the pros, these things are small. That one is 5 feet across. You know, I can hug the thing. You can set it up indoors. They're portable. Really low noise floors. Really low. They're very noise insensitive. I mean, that thing, even at Carnation City Hall, I couldn't hear the transformer repeats. There were other problems, but it worked. Cons, like as I said, these things are fiddly antennas, very narrow bandwidth. That antenna is, I think, 1.8 kilohertz wide for bandwidth before you have to retune.
So Shawn, is it a correct statement to say, if I'm looking through the middle of that like a rifle sight, that's the null direction? The actual direction is the actual metal round part?
Usually, yes. But the thing with most magnetic loop antennas is you have to be absolute perfect construction to have that null. If you do like most guys do and have twists or kinks in it, just because they don't want to straighten the pipe any more than that, the nulls go away really quick.
Mm.
It also makes the antennas harder to tune, but as a general rule with magnetic loop antennas, you're looking at a 5/8 diameter conductor minimum. If I built one of those with 12 gauge wire, it would only have maybe 130 hertz of bandwidth. Hertz, not kilohertz, hertz.
Don't a lot of operators use one of those as like a receive antenna and then use something else for transmit?
A lot of guys do. You can transmit with these. You just have to be careful because a variable capacitor is part of the construction of the antenna.
Yeah.
You have to use a capacitor that can handle the voltages and power you're putting out. Those antennas get expensive. These antennas are not cheap to build.
No, they're not.
If I build an antenna that can handle my linear, I'm looking at a $700 capacitor. Amusingly, it's Russian. The capacitor.
Imagine that.
I will say this, the Russian vacuum tube industry, those guys knew what they were doing. A vacuum variable capacitor out of Russia, those things are hard to find right now, and they are worth it. They are worth the extra effort because the Russia ones are always, they're dependable. I mean, quite honestly, if I have to pick a vacuum variable capacitor, I want a Russian one. Probably from mid-60s. They did those things very well. Can't say that about a lot of it. They did, but those things, yeah, those things tough. The good old Yagi. We have, it's basically a mini dipole with a whole bunch of parasitic elements attached to it on the plane. That red line, that's the only part that's connected to the radio. That's a partial dipole right there. Everything else is just pieces of metal. The important part is it'll bounce off the wider bits and go towards the shorter bits. And the more elements you have out on the boom, the longer the boom gets, the more directional that antenna gets.
The design of, or the length of the directors and the diameter and the spacing, really critical.
It can be, but I have also seen a planar Yagi where instead of a whole bunch of directors, it was just one flat piece of metal stretched all the way out. And it worked exactly the same. And it was heavy.
Yeah.
But it worked.
Do you have
I wouldn't want to build them.
that?
What's that?
A description of that Yagi from a piece of metal?
Yeah, I can show it to you later.
Mhm.
They're pretty easy. I mean, you basically do the math for the directors
Mhm.
and then just do a
like,
polygon,
like
do
whole
a
piece?
polygon out of sheet metal
Mhm.
that covers the external diameter of all the directors.
I got,
You're building a trapezoid with the directors. Well, just build one out of sheet metal. It works exactly the same.
I got to see a 4-element rotatable 80-meter Yagi. And guess what the rotator was?
Fire truck engine?
The whole tower.
Yeah, you rotate that at the base.
India embassy in Moscow has that thing.
Yeah, that's
So
They're rotating whole tower.
the pros with the Yagi, these things are directional. They're very high gain. They can be pretty noise resistant if they're built right. The cons are, well, if you want to use a thing to talk to more than one person, you need a rotor. Okay, so you increase costs again. They can be big. An 80-meter Yagi, that's huge. It'd cover this lot.
sure sounded good when you were listening.
Oh, yeah. All that gain, well, gain works on receive as well as transmit. I'm listening this way. I don't have to listen to the whole world, just a small bit. But, Yagis require aiming. The more precise, the bigger the Yagi, the more elements, the more precise your aiming has to be. And yeah, it really matters. A 14 element beam, that's got maybe a 7-8 degree signal path. If you hold your pinky out at arm's length, your pinky nail covers what that beam can hit. That's how accurate a Yagi can be. So being off by a few degrees, you won't hear what you're trying to hear. So Yagis are compromises. You can have as few as one director on a Yagi. And, that's just a case of what do you want to get out of it? How directional do you want to be? Next, please.
I was stationed in Montana at the Air Force Base. It was the backup to the hill and what's the big NORAD building? The big NORAD hill.
Mhm.
And they had a Yagi on top of that building that had to be 40 foot long, the boom, 40 to 50 foot. And it was, we never knew what it was. Of course, I wasn't in the radio.
60 meter.
Yeah. And it was pointed towards Colorado.
But this is a log periodic. This is actually the best diagram I can find for one of these. There are other diagrams that show the physical construction a little better. But basically you have two booms with what looks like a Yagi, but they're not. It's a sawtooth pattern, basically. Element over here sticks up this way, element over here sticks down this way. They are multi-band directional antennas. They are a little weird to look at, a little weird to build, but they work really, really, really well. Wide bandwidth. For directional antennas, a log periodic is going to have the widest bandwidth you can get without using a dish. Just because of the size of the antenna, because every element on that antenna is radiating. Versus the Yagi where just 2 out of many are radiating. So they're wide bandwidth, they got pretty good gain, they are directional. And just like a Yagi, the more elements you put on it, the more directional the log periodic gets. And by the way, the more elements you put on it, the more bands it can use. The more elements you put on it, the more bandwidth it has. But there's a diminishing return. You can get an antenna that has so much bandwidth, you can't hear anything because you're hearing everything. The more bandwidth you get on a log periodic, the more noise you get. And it again, when you get big, you need a rotor, you need a lot of support for it physically. They also, you reduce performance at lower frequencies simply because building one of these that has good performance on the low bands, they're massive. It's twice the weight of a Yagi on the same band for the same gain. The difference being is that Yagi isn't going to work on the higher bands. This will. So that's a log periodic.
Direction of signal is the same as a Yagi.
What's that?
The direction of the signal is the same as Yagi, the pointy end's the business end.
Yeah. The biggest way to tell them apart visually, a Yagi feeds near the fat end. A log periodic feeds at the skinny end. So your feed line is, if you see an antenna where the feed line goes out and connects all the way to the skinny point, that's a log periodic. If you see the feed line connect to the wide end, it's a Yagi. That's the easiest way to tell them apart. Now, if you're looking up the tower, hey, where's the feed line? Oh, it's out at the skinny end. That's a log. It's out at the fat end. That's a Yagi. And there is no exception to that. So, yeah, but log periodics need aiming just like every other directional antenna. And really, anytime you have gain in one direction, it's aiming. Now we're into the last chart, which is the middle one on the handout. Don't know why I did that. Talking antenna size. Okay, wavelengths for common bands frequencies. And this is the one that always boggles people's minds. On 80 meters, the difference between the top end of the band and the bottom end of the band, if you're building just a dipole, is almost 35 feet. That's a lot of wire. You build it for the center of the band. And then go back to the other chart, we talk about how much bandwidth we have. You cannot build a practical 80-meter dipole with enough bandwidth to cover the entire band without a tuner. A cage dipole for 80 meters that has enough bandwidth to cover the entire band is 14 feet in diameter. Would have to be at least 130 wires. That's a big, big, big antenna.
So Shawn, to make sure that we're all reading this correctly, on the 3.5, the 280 in the feet with the XXX is the beginning of the sine wave. It goes back to 0 and then to the end. So that's
all the way up, all the way back down to 0, all the way down to the other end of the wave, then all the way back up to zero.
Make sure,
That's 280 feet.
just wanted to make sure that we were on the same page.
Yeah, that's a single bandwidth at the bottom of the band. At the top end of the band, it's only 245 feet. But it's a big difference.
Trust.
Yeah. There are companies that make self-adjustable dipoles.
Called slinkies.
Those work too.
Yes, they do, actually, quite well.
But remember, slinkies are also loading coils.
Yeah.
Less common version of a dipole made with a pair of slinkies. They make great attic antennas. You impedance transformer in the middle, two slinkies, stretch it across your attic at the peak. They actually work. And if you suspend it on a wire, you can go up there and shorten or lengthen your spring. But that's what I got.